All right. So because this is a binary search tree, we can do a binary search on this, and binary search is basically going to solve this by using log of n. This is straightforward binary search question, and only thing is that we have to do a binary search for a tree. The binary search, what it says is every time we go through the tree, we have to split the tree into two halves always. So we are given a target. So this target is 3.7. Okay. Now this 3.7, we are going to compare with the root node here. If 3.7 is less than 4, okay, if 3.7 is less than 4, that means the closer number is going to be on the left side, or maybe 4 is the closest number. All right, maybe 4 is the closest number, but even if there is going to be any closer number, it will be always on the left side, because if I go on the right side, the numbers are going to increase. 5 is not closer to 3.7 than 4. All right, so that's how I split my tree. So I check the target. My conditions are basically, if target is sorry, if my n minus target, okay, let's take absolute value. Second, no, n minus target. If target is greater than sorry, my target is less than my node, then go left, okay, else go right. So that's it. uh that is what we want to do. Our target is 3.71. We check here, this is 4. Let's say our target was 3.12. Okay, let's say our target was 3.12. So check this 4. 4 is less than, sorry, 4 is greater than 3. That means I have to go on the left side. So I'll check here. 2 is now greater than, sorry, 2 is now smaller than my target. So I go on the right side now. So I check the right side. The distance is less. And then I'm already done. I've already passed everything. I cannot go further now. All right. So that's how we basically search in a binary search. That's what we have to do. We are going to start with binary tree here. Okay. So what we can do is while so we start from here, check the value, we go on the left, we go on the right, right? How long we want to do? We want to do it until node. Until node is not null. Okay, and I'm going to say node is root for now. Okay? If let's see at the value, if node dot val is, like we said, is greater than your target, okay, then node is equal to node dot left. Else node is equal to node dot right. All right. Every time we move the node, we just update our answer. So answer is basically going to say we want to return an integer, right? So let's say our answer is math.inf, the maximum number we have. So answer is equal to min of your whatever is the current answer, comma node dot val minus target. Going to get the absolute value of this. So this is going to give you the distance, right? One second. And we want to return the answer, right? So this cannot be the answer. This is going to give us the distance, but we want answer. So this is the distance, not the answer. This is the distance that we have. If distance is less than or equal to, if less than or equal to this, return, sorry, update the distance basically. Okay. Update the distance to be equal to this value. Okay. Your answer is basically none for now, and you update your answer here in this case. Answer is equal to node.val. Okay, that's it. Return your answer. Now corner cases here. The corner cases are when you have equal distances. So what we are doing here is we are going through the distance. So distance is initially infinite. So this infinite number is going to be 1. So it's greater than your absolute distance always. Okay, because we started out null. 4 minus your target, which is 3.7 in this case, is going to be zero point 0.3, and zero point 0.3 is less than your maximum number. So update the distance. So distance is now this absolute value, which is the difference between both the values. Okay. Then you update the answer because you found the distance which is smaller. All right. Uh, and then you just move on to the left and right. Now let's think about the case where you have a distance which is equal. So let's say you have 3.5. Okay. Now 3.5 is zero point 0.5 distance from 4 and also zero point 0.5 distance from 3. When you have same answers, then print the smallest number. So we want, in case of 3.5, we want to return 3. We start from 4. We get the 4. 4 is, we move on this direction. Then we move on this direction. Then we update the answer because we're checking greater than or equal to, right? So we are checking greater than or equal to. If it is distance is equal, we still want to update the answer, new value. Okay. Now let's take another example where the distance is, let's say, this thing where it will break. Is there any case that it breaks? So this is 3.5, it works. It is something else. What are the other cases? Your nodes are going to be this, your number of trees, at least one is going to be in the tree, so that's fine. Only one is present, then your distance is always going to be your distance from the root node, which works too. What about this case? 4.5, 3.5. 3.5 will go on the left, still find the answer. If it is greater, what about 4.5? 4.5, in that case, we update the answer, then we go on the right side. This time the distance is again equal, but our answer still should be the 4. It should not become 5. But here in this case, the answer is becoming 5 because we are updating it, right? So the answer becomes 5. Okay. In that case, let's do this. Uh, if it is greater, only then update. Okay. If else if the distance is equal, the distance is equal to your whatever the value that you have, then your answer is basically min of two things: min of answer, comma, node value. Okay. This should take care of that case. 4.5, in that case, you have to return 4 as an answer, right? So 4.5, when you want 4 and 5, it's okay. So this should run this. This works. Submit this. Good. So that works. Okay. So time complexity of this is O of n, because we are doing a binary search, n being total number of nodes we have. Every time we go on the left or right side, we are splitting the node by a log. So if you have 4 nodes, sorry, if you have 10 nodes, then we are only searching 4 nodes. So that's the log of n in this case, the time complexity. Move on quickly on the next one. Top k frequent elements. So given an integer array, return the k most frequent elements. You may return answer in any order. So most frequent element, if the value of k is 2, return 1 and 2, which are the most frequent. Okay. This is 1, then just return 1. Okay. It is guaranteed to have a unique answer. Okay. Complexity can be better than O of n log n, where n is the array size. Okay. Most frequent. So what we can do is we can go through this particular list and keep the count of each and every one. So 1 is present, let's say 3 times, 2 is present 2 times, 3 is present 1 times. Okay. And then Then to keep count, then you just have to sort the counts and get the values, right? So how do you get the values? You get the values from there. Okay.
सर डिफॉल्ट डिक्शनरी बनवली तर
We can take a default dictionary where one is going to have three, right? So default dictionary may
फर्स्ट
have three pointers. One is going to have
मॅक्स
three.
नंबर फ्रॉम दॅट आणि मग ती की डिलीट करायची जे मॅक्स नंबर आणि सेकंड हायेस्ट पण मिळेल मग तर के इज इक्वल टू 2 असेल तर लूप सेट करू
K is equal to 2 is you want to return two items, top two frequency.
Top two frequency. Yeah.
हा मग मॅक्स डिक्शनरीतली व्हॅल्यू पहिली गेट करायची ती की आणि ती मग डिलीट करायची मिळाली की आणि लूप 2 साठी सेट करणार के इज इक्वल टू 2 मग सेकंड हायेस्ट पण मिळेल आपल्याला मग मॅक्सच मिळेल ना परत मग ती 2 नंबर्स मिळतील
व्हॅल्यूज कसे आपण सॉर्ट करणार डिक्शनरीचे
डिक्शनरीचे मॅक्स की इज इक्वल टू डिक्शनरी डॉट व्हॅल्यूज म्हणून आहे मला वाटतं आहे असाइनमेंट मध्ये केलेलं आहे
so
डिक्शनरी मधून मॅक्स
one is two times, one is three times, okay,
3
and
times 2
two is present two times,
right
is present one time, okay. In this case what you want to do, you want to
right
sort the values.
हा sort values from
Sorry. Okay, values sort करना है. Values कसे sort करना है? These are the keys, these are values, right? How do you sort the values of the dictionary?
गेट कीज करून मॅक्स वापरायचं त्यामध्ये मॅक्स आणि ह्याच्यामध्ये एकच मिनिट मी होते
What you're saying is if you have this dictionary, you can go through the values. If this value is
मॅक्स देन गेट की
max get key, okay. If you get 3 here, then you check.
then we will remove the one number key and then again loop मध्ये सेकंड नंबर हायेस्ट येईल आपल्याला ती रिमूव्ह झाल्यानंतर तर सेकंड नंबरची की मिळेल
Okay, all right, so that will solve it in sorting, right? So if you sort it, it is going to be O of n log n, okay. Sorting, it's going to take O of n log n. So let's try to think. That is what we want, okay. So ठीक है, O of n log n, you want to sort this values, right? These are already sorted right now, okay. How do you get the top two? You iterate over the dictionary and then you get the, okay, fair enough. I think you can do that too. When you go through the dictionary, you want to sort the values first and then iterate through the keys using the values sorted, correct? So you want to say, let's build a counter here. Let's say the counter of nums. So this is your default dictionary. Okay. So let's call it default dictionary. Counter. Dot. You want to say sort, correct? You cannot sort a dictionary as far as I know. Okay. That's lambda. I'm not sure how do you. I'm pretty sure you cannot sort a dictionary. Search once.
सर मी एक मिनिट मी ते मला आता कोड नाही लक्षात येते मी सर्च करते तो असाइनमेंट मध्ये
This is there in assignment.
येस सर नॉट सिमिलर बट डिक्शनरी वापरून सॉर्ट केलेलं आहे मला आठवतंय आय विल लेट यू नो
Okay. So you have 3 here, you have 2 here, and then you have 1 3 here. So when you so let's say you have a dictionary, you keep count of how many times it is present. And one easy way is just to get a one easy way is to just use a what do you call that? A min heap, A min heap will work here because we are talking about top k. Top k usually solves with the min. So by keeping the counter, so we'll call it a dictionary counter as a counter of your nums, and you need a min here. Min heap equal to empty for now, and then for k comma your count in your dictionary counter dot items. Okay, get to the items here like this. What you can do is you can just add it to the main dot append. What you want to append to the main heap? You want to append, sorry, not main heap, heap q dot heap push. You're going to do a min heap. Okay, into the min heap, you're going to send two things inside. One is your count, and second is your value. Okay? So that makes sure that you get the count and value both. If the length of your min heap is greater than k, then you want to do a heap pop dot pop, okay? And you want to remove from your min heap. And your answer is basically going to be uh, what is present in your min heap. Okay, so get the min heap for you have counter and you have value. Okay? Min, you're only interested in the value. So that should be your answer. So you got heap pop length is greater than k. It is greater than k. You can pop it. What's wrong with this? Dictionary counter is count value of k. Dot heap pop length is greater than k. Length is 3. Then we have heap pop. And then what is wrong? What is count the value? Heap pop is not coming here. Why is it not coming here? One, what is wrong here? So you have counter, counter, no? One is present 3 times, three is present 2 times, three is present 1 times. Fine. top K. Right here. Silly mistake here. What's happening? Correct. The items. It's basically your key. And then count is it count? Oh, sorry. The key is getting updated here. The n value. And this K is already present here and it was getting updated. Silly mistake. All right. So that should work. So whenever you have dictionaries, make sure you take K as, and then you also have a K here. So that's what this would work. Okay, that works. So this is by solving using a min heap. I think you can also solve it in the n log n where you sort it by the values, and that should also work. I think. I'm not sure how I would go about with that. Yeah, I mean, one thing we can do is we can convert this into a list, which is going to look something like this, which is uh, what is the counter, and then what is the value, what is the count, and what is the value, then what is the count, then what is the value. Okay, you do this and then you sort this whole list, sort the whole thing, and just get the top last one. That will give you the top two also. That will also work. That will be added complexity because it's going to take O of n log n, where n being the total number of numbers you have. Let's quickly check the tutorial if there's a better way. Excellent. Actually, we have to learn that. So it's median of medians without a without a comma yes, it works in a different time, but constant alpha is too large. Alright. So let's move on to the next question. This is buildings with an ocean view. Okay. So the question says there are n buildings in a line, okay, and then you have to tell who are the buildings who are having the ocean view. So ocean is on the right side, I think. You are given an integer of heights. The ocean is on the right side of the building. So building has an open overview if it can, without any obstruction. So this is going to have an ocean view for sure. This is going to have an open shore because the next building is smaller. This is going to have an ocean over because next building is smaller. This is going to be having an ocean. Sorry, this is not going to have an ocean view because the next building is bigger than it. Okay, so the buildings who have ocean view are this, this, and this. All right. So what we want to find out is there any number bigger than 4 on the right side? Is there any number bigger than 2 on the right side? Is there a number bigger than 3 on the right side? Okay. What happens if the same building, same height, if the building cannot be seen without obstruction? Formally, a building have all the buildings on right have the smaller height. Okay, equal height रहेगा. Even in that case, it's going to be obstructing. Okay, so equal height also doesn't. So if this is 2 and this is 2, then that's also going to be obstructing each other. Cool. So we want to find if there's any value which is greater than or equal to that value. If there is no value which is greater than equal to this value, then it is going to be having an ocean view. Okay. So how can we solve this? So usually what we can do is we can just check this value and go all the items here and see if there's any number which is greater than or equal to 4. If there's any number who is greater than or equal to 4, then it does not have an ocean view. Then you take this value and check all the numbers on the right side. If there's any number which is equal or greater, then it's not going to have an ocean view. Go to this, check all of them. Go to this, check all of them. That is going to solve it in n square time because each element we are going to do twice. Okay. So 2 for loops are going to be required. That's going to solve it in n square time. Questions like this can also be solved by using a stack because once you see an item, you can remember its height and use that to your own advantage. So what we can do is we can use a stack and go from the right side. So what we can say, if the stack is empty, that means there is no item which is greater than 1 or equal to 1. Okay? After that, you push 1 into the stack. You check 3. Okay? You check 3. 3 is greater than your top of the stack, correct? So if 3 is greater than your top of the stack, then remove 1 and just put 3 in there. Okay? After that, you go to the next element. You can check 2. Is 2 greater than or equal to your top? No. So this becomes your I think you don't even need stack here. So you can start from here, check who is the biggest number. Biggest number is infinite, so this number minus infinity. So it's going to have an ocean view. Check this, who is the biggest number? The biggest number was 1. Now the biggest number is 3. Check this, the biggest number is 3 now. It is abstracting. Check this, the biggest number is 4 now. Haven't you? You just need one number, which is the biggest on the right. Biggest on the right. To start off with, biggest on the right is going to be minus of infinity, which is a negative number, really large negative number. Bit of infinity. Okay. And we are going to pass the height from the right side. For I in, let's call it building in range. Start from the right to left. We want to build our answer. So we start from length of the heights. Okay. Start from the length of the heights minus 1, go all the way 0. Reverse direction. Okay. If height of this current building, okay, height of this current building is less than, or if this height of this current building is greater than your biggest building on the right, then you want to put it in the answer. Answer dot append your building index. So that's an answer. Okay. After that, you want to update your biggest on the right here. Biggest on the right is equal to max of biggest on the right, comma, whatever the current building is. Keep on updating your max on the right. Return answer in reverse direction. Okay. So you have biggest on the right here. So let's take an example. Biggest on the right for this is 1. It's going to get added. Then you have 3, which updates the biggest on the right to 3. Then you have 2. Your biggest on the right doesn't change here, but 2 is not getting added because it's not having ocean view. Then you have 4. 4 is having 4 is going to update your biggest on the right, but at that point you're already at the end of the height, end of the buildings. Okay, so this should work. Right, so that works. Let me take a screenshot of this. The closest this is done. This we are going to check again, right? So Prachi, once we find something, just let us know. This we are done with. Range sum of a binary search. You're given a root node of a binary search tree. This is not premium, so you can access it easily. The given root node of a binary search tree, like I showed you earlier, left side is going to be smaller than the right side. All the elements on the left are going to be smaller than all the elements on the right side. That's the binary tree. Two integers low and high return sum of values of all nodes with values in the range of low and high. Okay, so you're given a range 7 and 15. Okay, so any value which is between 7 and 15, you want to get the sum of those. So if you check 7 here and 15 here, okay, so 7 plus 10 plus 15, because those are the three numbers which are in between 7 and 10. Okay. All right. So how can we use this information to go through this binary search tree? Okay. All right. So one thing we can do, which is fairly straightforward, is because this is the lowest number, go through the binary tree. Okay. Go through the binary tree and get all the numbers which are greater than 7. Okay. Go through the binary tree, get all the numbers which are greater than 7. And then go through the binary tree and get all the numbers which are smaller than 15. Okay. All the numbers which are smaller than 15. When you do that, you're going to get set of numbers. Then you can just do a intersection between those two sets to get the common numbers. Those two common numbers are basically going to be a range. That's one way of solving this. What could the other way be? Can we avoid doing this two-time parsing? So anytime we start here, we check this 10. Does this 10 fall in the range? If it does, add it to the sum. Okay. Then we have a option of going on left and right both. Okay. So we can do a DFS and add both of them. So let's add 5 and let's add 15 too. Okay. After that, once we are at 5, we check if 5 is within the range. If 5 is within the range, then we add it to the answer. If it is not within the range, okay, then we have an option of going on left or on the right. Okay, let's say 5 is not in the range, then how do we decide if it should be go on the right or left? So if 5 is smaller than the high and also smaller than the low, then you can go on the right side of the tree. Else, you cannot go anywhere. You just have to return from here. Okay. What about 18? So once you're at 15, is 15? Let's say this was 16. Okay, for now. So if this was 16, is 16 within this range? No, it is not. Okay. Is 16 greater than the high? Yes, it is greater than the high. That means you cannot pass it further. You are done. Okay. So yeah, we can do a DFS here on this binary search tree. DFS is going to solve this in O of n time. Worst case, you have to go through all the nodes. Okay. But I think we can solve this. O of n is fine. We can also solve this in log n time, where we search this and search this. But when we do the intersection, that is again going to be O of n. So yeah, I mean, we'll just go through the B of B. We'll just use the DFS approach here. Okay. So DFS approach, we want to use a stack because this is a tree. Use the stack. Add your tree to the stack. The kind of DFS we are going to use is pre-order, because at every item you're going to make a decision. So we can just do a pre-order. Your answer is going to start out with 0, while the stack is not empty. The stack is not empty. First thing we do is remove something from the stack. Stack.pop. What are we going to pop? We are going to pop a number here. So that is going to be a node. The node is getting popped here. All right. Now let's put our conditions. First condition is if node is between the value or not. So if node dot value is greater than or equal to your low, less than or equal to your high. If it is, that means you have your answer here. Answer plus node plus value. You add it to the answer. Okay, that's fine. Else condition is going to have your other conditions, how to navigate through this particular tree. Okay. Or you can just do a DFS and you don't even have to solve anything else here. Okay, all you have to do is just go through all the nodes and get the answer, which we can be more efficient here. So for example, if I just do this, stack if node dot left is present, then just do stack dot append node dot left, right, then just do node dot append, return your answer. This will also work. Okay, because we are just going through each and every node. When we do DFS, we have to put right first on that. Okay, this should also work. Uh, this will also work, but it's going to be more time consuming. Submit it will work, but it will be time consuming. Okay, we can save some time here. Okay, what's the time that we can save is we can be more strategic about adding things into the stack. Okay, all right. So let's think about the right side. So when can we add the right side to the stack? If okay, so uh, let's say I have to think if I should be adding 7 into the stack or not. For me to decide if I should be adding 7 to the stack or not, I have to make a decision using this node. If node dot val is less than my low, okay, if it is less than my low, then I can add the right side. Okay, and when can I add the left side? Node dot val is greater than my high. Okay, if node dot value is greater than my height, that means the inclusive side is not going to be on the opposite, right? Okay, so if 10 is not present in the range because it is greater than the height, that means none of this side is going to be on the range inside the range. So I can skip the whole 3 on the left side, on the right side, sorry. If 5 is already small, is not present in the range, that means I don't have to add this left side because this left side is never going to be in the range. So all I have to do is just add the add that condition. So this should also work. Okay. Expected not to be 10. Wrong here. We append right only if the value are not greater. It is less than. Only then add it. This is greater than. If this node is greater than my low, that means I can go on the left side. Sure. What you want. Okay. All right. So that was fairly simple question. You can also do DFS, or you can just do the strategic going to the node or not. Okay. So you can be more smart on what to add to the stack. Let's move on to the next question. Subarray sum equals to k. This is interesting. Given a subarray of numbers and an integer k, return the total number of subarrays whose sum equal to k. We have 1, 1, 1. The value is k is equal to 2. Summation of this 2 is 2. Summation of this 2 is also 2. So the total number of subarrays are 2. Okay. What about this? 3. So you have 1, 2. Okay. And then the other one is this 3 itself. So there are 2 again in this case. Subarray sum. Subarray is basically a continuous non-empty sequence. So yeah, one thing that comes to my mind is whenever you have this subarray sum and equal to k and all, subarray sums or anything related to subarray, such as like multiplication of a subarray or which is equal to a certain thing, you can use something called as a prefix sum. Okay. Or you can also, use a sliding window here. Sliding window are some of the easiest ones. So you can do a sliding window also. You can slide a window. We know that we start with this one, not enough. We add one more number into it. So enough to get to. So we got the answer. If it is going beyond the number, beyond the value, then we basically remove this item from your window. But the problem with that is your numbers can be negative also. So when you have negative numbers also, it will give you an issue. That won't work. Sub-array sliding won't work. Okay. So when you have sub-arrays, you have to use prefix sums here. So I'll just explain what a prefix sum is. So prefix sum basically means if you have nums here, which is 1, 2, okay, let's say 4. You have 4 numbers. So you create a prefix sum, which is going to be 1. Then you have we are 1. Then this is the prefix sum of 3. Then this is 5. This is 9. Okay. So what we are doing is all the elements before 1. Just have 1, put 1 here. All the elements before 2, summation 3, put it here. All the items before 3, summation is 5, so put it here. All the elements before 4, summation is 9, put it here. Okay. Now, this particular array is derived from this array. So you don't need this array any longer. Okay? This is not required now.
Sir, that 6 and 10 it comes, no? All the elements before 3 is 6.
Okay, yeah, you're right. 6 and
6 and 10.
correct, you're right. Okay. All right. So this array is basically created from, so this array is basically created from this array. Okay. So we don't need this information any longer. We can use this information now. Okay. All right. So how do we use this information? We can start by creating a dictionary. Okay. Let's focus for some time here. If I want to know what is sum of these two numbers, okay. If I want to know sum of what is these two numbers, one thing I can do is I can take the prefix sum of this number minus prefix sum of this number. Sorry, minus prefix sum of this. Okay, if I want to know what is the summation of these two, okay, if I want to know summation of these two, I can take prefix sum before this. So I can take 1 and I can take prefix sum of this number. 6 minus 1 is what? 5. So 5 is the summation of 3 and 2. 6 minus 1 can do that. If I want to get prefix sum of 2, 4, 2, 3, 4, all I can do is take 10 minus 1, which is the prefix sum before 2. If I want to get the prefix, if I want to get the summation of 3 and 4, I can take 10 minus this, all the numbers which are present here. Okay. That is also going to give me the prefix sum, all the numbers before 3 in subclassum. So if I do a prefix sum of 3, 10 minus 3 will give me the answer. Okay. So what I'm trying to say is your prefix sum of j, if j is this particular index, minus prefix sum of your I being your first index, is equal to prefix sum of your window that you have. You can prove that here directly. So let's say j is, so these are all 0, 1, 2. Let's put the index 0, 1, 2, 3 indexes. Okay? If the value of j is, let's say, 2, okay, so prefix sum of 2 is 6. 6 minus value of I is let's say 1. 6 minus 3. Second, P of j minus k window, right? So 6 minus 3 is value of I is as much, right? Value of I is 2. Sorry, value of j is, let me just put the numbers here. with j is equal to 2 and I is equal to 1. Okay. In that case, the window size is going to be uh, this I comma j. Okay. So not including I, but including j. So your window is basically having only one element, which is not including I. So 2. Okay. So I will not be included in this particular sum. So that is how the prefix sum basically we are trying to calculate. Okay. Is uh, your k is basically j minus I plus 1. Okay. So this is what you have. Your k is equal to j minus 1 plus j minus I plus k plus 1. This is your k. K is the window. Okay. Your size of the window. This is size of the window is 2. For size of the window being 2, your j has to be 3 and your I has to be 0. Okay. Let me just think. J minus, sorry, j minus minus 1, right? J minus, yeah. So that, 1 second, what is
So
happening here?
k is not window, it's a integer number equal to sum equals to k लिहिले.
Yeah, sorry. So your window size is basically this.
हाँ k p not pk is just k no.
So your
Sub
PK is basically prefix sum of your window.
okay total number of sub whose sum equals to k.
I'll just call it prefix sum of the window. What is present in the window? What is the prefix? What is the sum of the window? The sum of the window is basically this. This is what I'm trying to say. Okay. The sum of the window is equal to prefix sum of j minus prefix sum of I, where the window size is basically this value, j minus I minus 1. So 2 minus 1 minus j minus 1 should be enough. We don't need so complicated. So 2 minus 1, because this is 0 index set, right? That's right. That's your window size here. Okay, let's not complicate it further. So this is your prefix sum. This is your prefix. Your prefix. These are your nums. Okay. Prefix of j, which is prefix of 2, or this is 1. Window size is basically j minus I, which is 1. So you have window size of 1. Window size of 1, which is only this value. Okay. So these are the indices that I have. Okay. So without getting confused, so j is 2, okay, I is 1. So we are talking about this. I is 1. Okay. So the window is only this much. So this is your window. This is your window. So 6 minus 3. Answer is 3. That is the size of, that is the sum of your window. Okay. Now let's take this value of j as 0. Okay. Let's take the value of, sorry, value of j as 2 and value of I as 0. Okay. In that case, what happens? Your window is basically this much. 2 and 3 is your window. Okay. These are your numbers and 2 and 3 are your windows. In this window, what is the sum? The sum is 5. Okay. How can you get this 5? You can directly use this prefix sums. 6 minus value of I is 0. Correct. So j is 2. Value of I is 0. 6 minus 1 is going to give you your prefix sum, or your window, sorry, or you give you window sum here. This is actually simpler to explain if I just use let's say you have this number line. this number line. Now starting from here all the way to here. If I want to know how much is this distance, and if I know how much is this distance, and if I know how much is this distance, okay, I can get this distance, correct? Total minus whatever is this distance is going to give me this particular distance, correct? You're getting what I'm saying? So we can use this particular concept. That is what we are doing, right? So this is the prefix sum of all the way till here, and this is the prefix sum of all the way till here. So total minus this much value is going to give me this. So this is my window sum. Okay, this is my window sum. Okay. So given that information, let's proceed now. So what we can see, we can check if we have seen something. Okay. Now we can change this equation to something like this. Let's change this equation to P of j minus some window is equal to P of I. Okay. And this will also be true. Okay. This will also be true. What is some window? Some window is basically this k value that we're trying to search. Okay. Because we want the sum to be k. Correct. So the sum to be k. I'm just going to say k here for now, like this, just to keep it consistent with the question that we have. Right. So we want to get this particular thing. So every time we go through, now what we are going to do is we are going to pass through this prefix sums. Okay. 1 minus k is how much? Minus 1. All right. And we are going to keep track if we have seen it or not. So whatever we have seen, we'll put it inside a dictionary, which we call it a seen dictionary. If we have seen the sum, then we put it into the seen dictionary. The concept is whenever we see a sum, we just put it into the dictionary. So first thing that we see is P of the, so we start from here, right? So we are going to pass this whole prefix sums. Let's keep this here. So we start from 1. 1 minus your k is minus 1. Okay, minus 1 is not present here. So nothing we have seen. So what we have seen is we have seen 1. We have seen this prefix sum, right? We have seen this prefix sum. And how many times we have seen this prefix sum? We have seen this prefix sum only once. Okay. Next, we go to 3. 3 minus your k is how much? That is 1. Okay. 3 minus k is how much? That is 1. All right. This is 1 is right. We have seen this once. Second. So what we are doing is we are doing this. Okay. P of j minus sum. So j is 3. 3 minus 2. We have seen this, right? So because we have seen this, we are at the second element, right? We are at this window. Oh yeah, we have seen it, right? Sorry, we have to update now. Correct. Okay. So now that we have seen this particular, so what happens is we go to 3 and we say 3 minus k. 3 minus k is how much? 1. If we have seen that item, okay, if we have seen that item, then whatever is the count, that is the answer that we have. Okay. So we have seen that item. So that means our count, which was 0, it becomes +1 because we have seen this one. Okay. We have seen it one time. That's why. So this is your prefix sum and this is the frequency, how many times you have seen it. So Now we have seen 3 and we added 1 because we are only seen a prefix sum of 3 here, right? We are seeing 3 and we add it here as it is. Then we check 6 minus your window, which is, uh, what did we say the window was? 2, right? Value of k is 2, correct? So 6 minus 2. 6 minus 2 is how much? 4. 4 is not present here, so nothing to do. So then we add 6 here. Okay? Then you again check 10 minus 2. 10 minus 2, 8. 8 is also not present here. Then you add 10. It's present only one time. Okay? So your answer is 1 because your prefix sum of 2 is only possible with this. Okay. Now let's change the value of k to something else. So let's say value of k is, let's take two values which will match here. So let's take 3. Okay, value of k is 3. Just run this one last time and then we'll write the code. Okay, so we'll update this scene and we'll also update the answer. So what happens now? Okay, so we start out with this being empty. All right, with that being empty, first thing we check is what we are parsing. So we are parsing 1. Okay, 1 minus 3. It is how much? Minus 2. Minus 2 is not present in the scene, so nothing to do. So 1 we saw once. Okay, how many times we see this? We saw it once, so add it once. Okay, after that we check 3 minus 3. It is 0. Do you have 0 here? No, you don't have 0 here, right? So that will become 3. We have seen once. Okay, all right. Next, you have 6. 6 minus 3 is 3. Are you seeing 3 here? Yes, I'm seeing 3. So add 1 here. All right. Next, you have to add this, right? We have seen 6, so add 1 here. Then we have 10. 10 minus 3 is 7. 7 is not present here. So just don't do anything. 10, 1. Add that here. So your answer becomes 1. The problem with this is you are missing this initial value. If the window is present in this initial, it is not being seen here. Okay. If 0th element is present in the initial, it is not being present there. So in order to fix that, you have to initialize the scene with 0 colon 1. This will make sure that your initial is also getting added. So what is happening is your prefix sum is including the initial value also. Okay, so if your window is having this 1 plus 2 is also 3, right? But your answer came out only 1. Why is that? Because when you were at 3, you said 3 minus 3, you didn't have 0 present here. Okay, you said 3 minus 3 and you didn't have 0 present there. That was the issue. So that's why you have to initialize it with 0 colon 1, where 0 being the check for making sure if the window includes your first value. So let's code this. Complex. We've seen that we need prefix sum, which is length of your nums. We can improve this one also. Okay, I'll just tell you how to improve that. So prefix sum is that for n in prefix sum I. Let's do one thing. Let's add prefix sum 0 already. So prefix sum 0 is basically your nums 0th element. Okay, and then let's do a skip the first element so that we can do prefix sum, which is I minus 1 first element plus n, whatever the new element is. So these are my prefix sums. I got my prefix sums now. Now I can iterate through the prefix sum. So if for p in my prefix sum, okay, the situation is really simple here. We have to just make sure that we have scene, which is already added here. Let's add the scene here because it is required here. Okay. If your prefix sum minus k is present in scene, okay, then your answer is basically uh, whatever is the value that you're seeing. Scene minus k. That's your answer. Okay. And you want to update your scene with the prefix sum to be equal to if it is present, scene dot, you can just do get here, p, comma, if it is present, get the value of p. If it is not present, get 0 plus 1. You can do the same thing here and just say your answer. But let's keep it like this because I want to show this concept of if this is seen, okay, only then do it. And then return your answer. Your answer is basically starting out with 0. Output came of 1. Sum p is present here. इसे गलत हो गया क्योंकि वगैरह तो नहीं है. If some minus k, it is present in the scene, then there is a value of scene. It's minus k. Add it to the answer. Initialize it to 0. That's fine too. Some p minus k in scene, right? Scene p minus k. Get that value. Scene p. Get that value too. Add 1 to it. It is not present. It's wrong. Prefix sum 0 is equal to nums 0 is correct. Start with this. It's correct. I minus 1 plus value. Let's just check prefix sum once. Prefix sums. Okay. Why is this 0? Oh, this. So, it is going to enumerate wrong. Range length of 1 comma length of nums. Okay, to do that because this index was becoming 0 here. Right? It's just creating all kind of problems. I don't know why didn't it throw out of index here? This is basically nums and your prefix something, right? Now your prefix sum is right 1, 2, 3. Works. Okay. All right. Let's try to optimize this a little bit. Time complexity of this is O of n. Space complexity is also O of n because you're using this prefix sums. Now, this prefix sums that you have, you don't really need this prefix sum, okay? Because at every point, you're just checking the prefix sum at that point. So all you need is the current sum. You don't really need this prefix sum. This prefix sum is only here to explain it properly, but you don't really need this prefix sum. You just need the current sum. If you can get what is the value, what is the sum till the current value, you're moving on ahead. Okay? You're not storing anything from the prefix sum. Okay, once you have the value of p, you're only using the p once. Okay, you're using the value of p only once. After that, you're not reusing it again. Just need current sum. Current sum is 0, and you can just iterate through your nums directly. N. Okay, and what you can do is you can just check this. Okay. Current sum plus is equal to n. Update your current sum using the value of p. Okay, now n, sorry, n not current sum, because that is what your p is. So current sum minus k in the q, in the same thing. Everything else remains the same. Now this is no longer p, this becomes n because you have numbers there. This becomes your current sum. You are changing p to the current sum directly. You don't need any of this. Okay, all you need is the current sum. If you have the current sum, then you can use the current sum directly here to get the prefix sums till now. And if it is present in the scene, you add it to the answer. If it is not, you don't add it to the answer. Works. Okay. So very good. Is there anything else given here? Talking about increasing, decreasing. Let's move on to the next one. Yeah. So the question is binary tree right side view. Okay. Not premium, right? So you're given a binary tree, and imagine that you're seeing it from the right side. If you see it from the right side, you're going to only see these three nodes. These are going to get hidden. So what kind of okay? So if you check this, then when you check on the right side, you're going to see only these nodes. You're going to see 1, 3, 4, and 5. Okay, everything else is not going to. So as you can see here, the diagram itself shows that this is a level order traversal. Level order traversal, you have to BFS traversal. So level by level, you want to traverse this particular tree. When you want to do a level order traversal, you have to use BFS. Okay, so you start with this particular level, keep on doing the BFS. Okay, and whatever is the last element that you are seeing in that level, add it to the answer. The answer expected is list of integers. So let's just create an answer. Because this is the breadth-first search or your level order traversal, if you want to use the queue, it's empty for now. You're going to append the root to the queue. Okay. After that, you are going to iterate it while your queue is not empty. Get the node which is present in the queue. Okay. Or at any given point, the queue is going to have the items. Okay. At any given point, the queue is basically going to have all the items in that particular level. Okay. All the items in that particular level. Okay. Again, at any given point, the queue is going to have all the items in that level. Okay. So when I check the node, which is basically queue dot pop left, it's going to pop left. So one is getting popped out of the queue. You have 2, 3. So one is getting popped out of the 3. One has to be added to the answer. So one gets added to the answer because that's the only element. After that, I go to 2 and I go to the next level. Before I go to next level, I need to add left and right of the queue, left and right of the 1 to the queue. So let's do that. If node dot left, then queue dot append your node dot left. If node dot right, then node dot right is getting appended to your queue. Okay. So you go here, append this and this. You have to append this because these are the items which are below this are going to be your right side. Okay, you appended left and right both, and now your queue is having these two elements. Okay. After that, you go to this particular element, and then you add next two things into the queue. This, add next two things to the queue. Okay. So what we can do is, since we know that at any given point, the queue is basically going to have all the items in that one level. Okay. So, uh, while popping, so we can iterate through that queue fully in range, length of the queue, and iterate through the queue fully so that we can pop each and every item. Okay. So each and every item is now getting popped from the queue, and its children are getting added. Okay. And your answer is basically going to be whatever the last item was popped from the queue. Node dot value. Okay. So your answer is basically going to be whatever the last value that was popped from the queue. So when one was added to the queue, you are going to have in the queue only one item, which is one. That is your queue. So iterate through the queue. Value of node is going to be one, and then add it to the answer. So one got added to the answer. Yeah. So one got added to the answer. Next, you go to the second item. You add. Now your queue is having 2 comma 3. Okay. So your queue is having 2 comma 3. You went to 2. You popped it. You check who are the children of 2, and then you're adding things to 2 with to the queue, which is 4. And then you go to the second item in the queue, you pop it out, but you're only going to pop it 2 times because you are already making sure that you only go to the range of the length of the queue before you keep adding the items. Okay. Before adding, you're ranging it. You're making sure you only go till the level. Don't go beyond that. You're not going to the 4. That make sure that you already have those things in your answer. Answer. So this should work. So you have answer dot append, node dot value, everything is right. This is not double. We didn't check this corner case where this can be null. Okay. If that is null, then return empty. There you go. Now it passes. Okay. Time complexity of this is O of n because we are going through all the items. Space complexity of this is again O of n because we are using this cube. Okay. It is not going to be O of n, but because at any given point you are going to have only few items in the queue. Uh, but yeah, space complexity and time complexity O of n, the worst case. To the next question quickly. Moving average of a data stream. We are given a stream of integers and a window size. Calculate the moving average of all the integers in the sliding window. Implement two functions, which is moving average and what is the next. Moving average is basically class name, and you want to get the next, which is moving average of the last size values of the string. The explanation here is we have 3. Then moving average, whenever you get the next, you get a value also. This value gets added to the list. Okay? So it goes like this. We have 3, which was initialized first. Okay? After that, 1 was added. Okay. When 1 was added, before adding 1, Okay, so I think so initialize the object with size of window size. Okay, so what it says is when you initialize it, you say what is the moving average that you want. I want a moving average of size 3. Okay. When you say next, you're going to send an item into it. So now I have an item 1 into it. Because there's only one item, the moving average of this is 1. Okay. After that, next 10 is sent. So when 10 is added here, the moving average of this is 11 by 2. After that, 3 is sent. Moving average of this is 1 plus 10 plus 3 divided by 3. After that, you have 5 that is sent. The moving average is basically only last 3 elements. Okay? Don't use all the ones, only use the moving average of last 3 elements. So what can we do here? So first thing we know that we have to initialize the window size. That's fine. If you want to get the sum, you just go, just take last 3 items in your list and you get the answer. Correct? The question is, do you really want to save everything? Let's just check. What is the constraint? Size is 1000. Value can be 10 raised to the power 5. At most 10 raised to the power 4 calls will be made to the next. That's straightforward. So all we need is we need one self dot size, size, okay, and then we need an list to maintain, right? So numbers. This is what you need. This is what you need. Anytime a new item is added, all you have to do is dot append value to it. Okay, and when you return, you can just return self dot nums. Last 3 elements. That's last 3 elements for you. Take sum of this divided by not last 3, last self dot size. What are the sizes? Size is 3, then then 3. Then divided by whatever is minimum. Okay, whatever is minimum of the sum of size and your length of this. Because when you have only one item, you have to divide it by only one. Okay, length of your whole thing. Let me just first of all send a screenshot to you. You can optimize this. Okay, talk about the optimization. Try to optimize this. So all we did is we just first initialize what is the size. Size is given to us whenever we initialize. The size is initialized to 3. After that, we just keep on adding items to this particular nums, and then we have our answer. Okay, we just take the sum of last 3 elements and then return the moving average. Okay, now what we can improve here is, do we really need to store all the numbers, or can we only store whatever is the size? Correct. So what we can do is we can convert this to a, okay, so this makes sure that we have a queue, which means whatever is added first will be removed, so that we don't have more than key size. Okay, so we can check here if the length of your nums is greater than self dot size. Okay, if it is greater than your self dot size, then do one thing: pop it. Dot pop left. You don't need that number anymore. Right? Remove the one which was added. Should also, this should optimize it. What happened? Oh, this DQ. Okay. Once when we this is DQ, it is going to create problems for us. Okay. So we cannot do this sequencing like this. We can just do a sum directly. Give you a sum. Okay. You cannot do slicing on a DQ. It's a double. It's the double Q, which in fact internally it's a double linked list. You cannot do a slicing on that. All right. So it should work. There you go. That worked. Can we improve a little bit? It's so bad. What else can be done? If you have a doubly linked list, anytime the size becomes 10, you just pop it out of the linked list. Sounds like a pair. Yeah, I think it's fine. Sometimes it's just better. Let's check this answer. That's smart, actually. So what they want to say is keep a Windows sum always, okay, and use that sum. You don't really have to know how many items you're seeing. Okay, so just keep a sum, and that sum should give you everything. Okay, so what they're saying is keep a sum of zero, start out with, and keep a size of how many you've seen. Okay, so window size, start out with, it is zero because you don't have any items. Okay, this is window sum. Okay, we already know window size should be, so just quickly up. So window size. So what they're saying, just make sure that you only have 3 items in there and not more than that. So just use a window sum directly. So anytime you see a new number, make sure you update your window sum. Window sum is plus value that you added just now. Okay. Okay. So that's your window sum. Now what? How do you remove it? Okay. So I'm going to call it self dot first value in my window. Okay, because I want to remove it. So first value of my window because I'm going to remove it. I think first value of my window because I want to remove it. I want to remove it only when my window size becomes greater than my size. Okay, start out with window size is 0. Okay, what's my window size now? My window size is +1 because I'm adding a new value +1. So my window size increased by 1. Okay, at any given point, if my window size is greater than my self dot size, which is the maximum size I need, if at any point if this is happening, then remove the first value that was added. Okay, remove the very first from the window. Store the first value. So basically, what I want to say is let's subtract this minus. You want to subtract the value that was added earlier. This is the first value that was added to the window. I keep on sliding it. My last 3 scene values, right? My first value My first value when I add it, it's 3. After that, it's still 3. Then it's 10. But then still, sorry, it's 1. Then it's 10 because that's the sequence in which I'm inserting. Then it is still 1. Then I went to 3. It is still 1. Then I went to 5. As soon as I go to 5, that value has to update to 10. But I have not stored 10 anywhere, correct? Let's just check this editorial once. I have not stored 10 anywhere. Something else. Here, what they're saying, we're given 1, 10, 3, and 5. Okay? So if you ask me what is this Windows sum here, so it's going to be 1. You ask me, this is going to be 11. Okay. You ask me here, it's going to be sum of all of these. If you ask me here, then it is going to be what we do. All right. Anyways, the values. He's also using a WQ, right? What about this one? He also is using a WQ. They're also doing the same. Oh, he's
They are
removing.
removing the 0th element.
Okay, he's removing the. No, we are also removing the W linked list item. But when he removes it, he's also subtracting the current sum. So what is happening here is this is fine. Okay, this works now. Know that this works. All right. So he's maintaining one more thing, which is the uh, window
Windows sum.
sum is equal to 0. Okay, and this window sum is basically this thing, plus 0. Sorry, plus val. Okay, and then whenever it's time to remove it, let's update the window sum to something else. Window sum minus whatever was popped from here, right? Whatever value was popped from here, do a subtraction of that. Whatever was popped, subtract it. And then you don't need the whole thing. Window sum here. So just need
Hmm.
window sum
So,
here. And this is still fine. Enough size and length. Okay. Okay, put such. Let's see, we can do one more. One more. We did. Yeah, question, go ahead.
सर ते के फ्रिक्वेंटचं जमलं ते करायला डिक्शनरी गेट की
Did you send it?
तर चॅट ऑन चॅट
Chatting. Okay.
ओके
See, actually, is it on the Discord or?
No, I will test it here in this chat.
Okay.
Just a minute.
All right. So let's take a look at this. Which one was that? Top keep.
K frequency.
So what you did, you create a dictionary. After that, you have an output here, and then you okay.
Frequency count.
Frequency count. So first you take the dictionary. After that, what is this number in set of numbers? Okay, you convert that to
Numbers of frequency count, each number just.
oh, this is just frequency count. So this is counter. Okay, so you got the dictionary. So that max count is equal to max of dictionary. We are iterating through the dictionary here, right? Okay.
Right.
You are iterating through the whole dictionary.
Right.
And the key is the value. Maximum out dot append max count. Okay. Yes, your dictionary one is removing. Okay, you remove it from the count. Okay, makes sense. Number of max count. Yeah, I think this also looks right. I mean, yeah, I mean this also is correct, Prachi. This is also of n log n. So time complexity of this is so this is not O of n log n. This is O of n into k. Okay, because you have a loop of k here, and this max is basically going to go through all the elements to find the max. Right? To get the max, you have to go through all the elements in the dictionary. Correct? So this will be O of. We can submit this. I think this will work.
Submit it slower, but what's
Yeah, it is slower because of the time complexity. This one has a time complexity of n log n log k. Sorry. Let's remove this print. But yeah, I mean it's the right solution, Prachi. The right acceptable solution.
okay?
All right, let's do this quickly. So, removing the nth node from the end of the list. So what you want to what is you want to remove the nth node from the end of the list. So you want to remove the second from the right. That means you want to remove this 4. Okay, right? What if we want to remove this first item? Point directly here. All right. So what we can do here, whenever you have going to the nth or uh, something like that, we can basically first of all think how can we reach here? Okay, because we want to remove this, right? In order to remove this, we have to reach here, and in order to remove this, you can just do dot next of this is equal to next of this directly. So this will get removed directly from here. So how can you reach here? So in order to reach here, we can start a pointer from here. Okay, and start another pointer. All right, keep moving the second pointer all the way till you reach n. So let's say you want to remove second item from here, right? So keep your first pointer here, keep your second pointer also here. Increase only second pointer so that it goes here. Now your second pointer is here. The distance between your first pointer and second pointer is n or 2, because both of them are separated here by one dash here, right? Now at this point, keep on moving both the pointers together. How long do you want to move it? Until your second pointer goes beyond this list. That means your first pointer is going to stop here. Or when your second pointer goes to the last of the list, your first pointer is going to stop here. So your first pointer stops here and you already have the answer. So that's the key of solving this one. Okay, so let's start with the 2 pointers. So pointer 1, but yeah, there's a corner case. What if you want to delete this one? So what if they say delete 1, 2, 3, 4, 5? Delete fifth node from the start. Then you don't have any pointers to remove. Starting from here, you want to remove this pointer. You cannot remove the pointer on which you are on right now. So you need a dummy head here. So let's have a dummy head. Dummy head is basically a list node which is going to have some dummy value in it. Okay, and your dummy head dot next is equal to your head. Okay, okay. Okay, now point your both the pointers to the dummy heads. So your P1 and your P2. Okay, P1 is equal to your dummy head and your P2 is equal to your dummy head. Both of them are pointing to the same head. Okay, now while your P2 is still not none, that means you are not reached to the end. Do one thing. P2 dot next is equal to P2 is equal to P2 dot next. So second pointer is getting added to the next item. All right. How long do you want to do that? How far is P2? So P2 is at the same distance right now. Whenever you do this, P2 plus 1. How far is P2 from here? If how far is P2 is equal to n. Okay. Give me a second. On increasing this, when do you stop? So you stop at point. Give me a second. Start iterating P2. You keep on moving P2 until it reaches the end. You make sure that the distance between P1 and P2 is n. It is not beyond that. At any point, if that becomes n, you have to increase. Okay. Okay. If that has reached there, then your P1 is equal to P1 dot next. Right? Else, keep on increasing your how far is your P2 until the distance between them is becoming n. So both of them are starting at the dummy head. So they're both of them are starting outside. So dummy head P1, then you have P2 here. Okay. Distance between both of them is 1. Then your P2 reaches here and your P1 is still pointing there to the dummy head. After that, keep on moving both of them together until your P2 reaches out of the list. When your P2 is out of the list, your P1 should be pointing to 3. Is that happening right now? So let's take this list here. Right? So we have 1, 2, 3, 4. Okay. P1 is at 1. Your P2 is sorry, not at 1. We added -1, right? So your P1 is at -1 and your P2 is also at the -1. Okay. You keep on increasing P2. So the distance is 0 between them. P2 increased, distance became 1. P2 changed to P2 increased, distance became 2. P2 went to 3 now. Okay. All right. So your P2 is pointing. Sorry. Second. This is -1 both of them, right? So your distance is 0 for now. You moved P2 and you increase the distance by 1. So your P2 is pointing here now. Okay. So let's write P2 is pointing here. You moved P2 and you increase the distance by 1. So, okay. So your P2 is pointing there and your distance is 2. All right. Now, this is what you have. Let me just put this -1 here so that you can easily understand what's happening. So this is what your linked list is. So this is the whole window. Okay. So this is the whole window. When you move both of them together until your P2 becomes null. Okay. So your P2 becomes null at this point. At this point, your P2 becomes null because null is here, right? So your null is here. So your P1 is pointing here. So you don't want that. You want P2 dot next is available. Until P2 dot next is available, keep on moving that so that your P1 points here. Okay, there you go. So your P1 points there and you just keep on going until your P2 dot next is available. All right, now once you are there, you know that you want to remove the item which is next to P1, correct? So your P1 dot next is equal to P1 dot next. Okay, let's check what's happening. You want to remove the item which is next to P1. Okay, so removing item next to P1. So if your P1 is here, removing the item next to P1 is basically removing this link and moving it directly here. So this will remove the item which is intended. Okay, you have to return something. You don't have to return anything, right? Given the head, remove the nth node from the end of the list and return its head. You want to return the head. Return head as it is. You're not changing anything. Okay, that sounds good. Now, what are the corner cases? When you want to remove, let's say you only have one item. You only have one item, you want to remove this one item. Your dummy head is here. So this is what your linked list is. You start from here. P1 is pointing here, your P2 is pointing here. This become 1, this became 1. You want to remove the item, which is this item you want to remove, right? So your P1 is pointing to null directly. Okay, so you want to just return dummy head dot next. So what your dummy head is dot next. That is your head. If the head node itself is removed, then it is going to point to the item which is after the head. This is what is required, I think. Okay, there you go. So that's what is required. This works. So pointers, whenever you see linked list or pointers, you can start thinking from a point of view of using a dummy head like this. But just make sure that you hand run it properly before trying it out or before submitting. Practice. Can we do one? Still got time. So you remove this, merging the intervals. All right. So the question says an intervals is given where you have start and the end. You want to merge all the overlapping intervals and return an array with non-overlapping. So you have this 1, 3. This is overlapping with this, right? So these two are overlapping. We have to merge these two together to get 1, 6. After that, these are overlapping. We have to merge them together to get okay. All right. What else is given? Cover. Do they say anything about the sequence here? Nothing about the sequence, right? So what I'm trying to say is can 26 be before 13? And that's also a valid input. We can check that quickly. So we should ask that, but yeah, let's just check that. Okay, so this is an acceptable answer. This is an acceptable input. So we have to take care of that. Okay, is it? I think that is what is happening. That is also acceptable. So 2613 810. We have 26. Is this acceptable? Let's just check one more thing. It's 15. This also work. Okay, there you go. That works. Okay. All right. So first thing that we saw here, that this intervals can be in the any order. So one thing we can do is we can just sort this in such a way that we have the smaller ones on the first and then the increasing pattern, so that we don't have to worry about some like this, right? 1518 is coming first. So move this 1518 to the right position first, and after that try to merge it. Okay. That makes sure that your start is always smaller or equal to the start of the next particular interval. Okay. The first thing we can do is sort the intervals. Don't update the input that is coming to you. Maybe choose a different one. So intervals are sorted now. Okay. All right. So that's one. We need an answer. So let's just keep an answer here, which is like this. So let's think about how to merge this. So you are given these two. Okay. You want to merge these two together, and whatever is the output of these two can be merged with the next one, if at all it has to be merged. Okay. Whatever is output of these three can be merged with the next one, if at all we want to merge it. Okay. That's the whole idea of this.
Intersection we can take, right?
Intersection will not give us the merge, right? You have to do a union.
Union, okay.
Correct. So
Yeah.
intersection is common stuff. Okay. So you want to do a union here. You're right. You want to do a union of these two. Okay. But when we do the union, we want to get the minimum and the maximum only. Okay. And we want to make sure that union is only possible when this 2 is basically between 1 and 3. That's why it is possible. Correct?
Yeah. Well, any one element should be in between. Right.
Yeah. Any one. So this 3 is between this. That's why it is possible. Okay. Then that is one way of looking at it. Okay. All right. So what we can do is, let's say we have a starting interval, which is this. Okay. And we try to merge things into this. So in order to merge into this minimum has to be between here. That's one condition. Okay. This minimum has to be present between these values. If not, then it cannot be merged. If not, this cannot be merged. So this will go into the answer directly. And then you take this as your new item that you want to try to merge with others. Okay. So you have this particular list. You take this, you start out with this. So you say, okay, I'm trying to take this and merge with next. So when I try to merge it with next, I see that it can be merged. So these two will be merged and the answer is 1, 6. So now I'll try to use 1, 6 and try to merge it with the next one. Okay. If it cannot be merged, then I have to put 1, 6 here. And then my new thing that I'm trying to merge is 8, 10. Now I'll take this 8, 10 and try to move, try to check, can this be merged with the next one? It cannot be merged. So put this 8, 10 here. And then again, this is going to be present my new item that, or new interval that I'm trying to merge with the next one. Okay. So we need to initialize. Okay. Something which we're trying to merge with the next one. Okay. So we can call that as try to merge. I'm not sure what to call it, but I just try to merge. Okay. Try to merge is first of all we start out with the initial one, which is the zeroth interval directly. Okay. That's one. That's just okay. Now you want to go through each and everything. So you want to go through the intervals. So I'll just call it intervals. Okay? You don't want to go all the ones you because the first one you already added here. Okay, or you can also add the first one again. So when if you start from here, that's fine. Okay, so we can say we are trying to merge this. Correct. So since we're trying to merge this, how do we merge it? If this inter lower value of this is between try to merge 0. These are closed, right? Return interval, both of them are closed. Okay, it is this. Okay, if this is true, then it can be merged. Correct. So this can be merged because this 2 lies between this. All right. So your try to merge is basically going to be two things, which is try to merge 0 as it is, and then maybe your new interval high side. Okay, or your new interval second value that you have. So this is what your try to merge is going to be. Okay, so that's one. Else if. Okay, let's say this was so let's say this was 1 comma 2. Is that the only condition to merge? I just have to check this 2 is lying between this, only then merge it, or else there's no need to merge. What else can be checked? So 1 comma 10.
Just check one element. Is it, if it is that, then just merge it straight away. No need to check other. No.
Let's think about any corner cases that we may have missed. Okay, so we know that these two cannot be merged, that's for sure. We know that this can be merged because this 4 is here, and it can be merged. Okay, what else? 3 can be merged. So we only check this first element, right? Yeah. So we try to merge it there. Uh, else this answer dot append your try to merge, and then your try to merge is basically your new interval that we have. Okay. Return your answer. Now let's think. You try to merge this, right? Let's check this answer. You try to merge is 1 comma 3. You go to 1 comma 3. Your 1 comma 3 is present there. So your 1 is basically between 1 comma 3. So if you just say true and you try to merge is going to be 1 comma 6. Sorry, 1 comma 3 again. It's fine. So next you check with this. So with this value is between here, which is true. So your try to merge is going to be 1 comma 6. After that you check 8. 8 is not between 1 comma 6. So you're good. No. That's because we skipped the last one. Okay, so when we are at the end here, okay, so when we are there, we have to make sure that we add this also. Okay. Try to merge becomes enter. This thing appended. Okay, so you have to check the last element. If your answer -1 is not equal to try to merge, then you have some extra element that needs to be added. That append, try to merge, which is your last item. Okay. So it's not answer is out of index. What test piece is this? How about that? We are missing this case where we have to merge this whole thing, right? So 1 comma 5. You have to add this because this is present in try to merge. This is present in try to merge. What condition makes me to add it? I cannot add it here. Directly add it. Directly add it. Uh, work in this condition, but I'm pretty sure it will fail in one. The condition that I'm trying to check is where we have something like this. Just quickly check that condition. 1 comma 3. We have 4 comma 5. You try to no, it will work. It has to be max of something. This has to be max of try to merge one.
Try to
So
merge.
try to merge one. That's what we want. What else we miss? Did we miss anything else? This condition, right? 1, 4, and 3. It's better. All right. Time complexity is O of n, n being total number of intervals that you have, and space complexity is time complexity O of n log n, because you're sorting here. So time space complexity is O of n, time complexity is O of n log n plus O of n, but the main one is this O of n log n. So this is going to take the most time. Everything else. All right. I think we can stop here today, and then we'll continue tomorrow. Thanks, everyone. I'll see you all tomorrow. Yeah. Bye bye.
Yes. Bye. Thank you.
Yeah.
Yes.
Bye.